Integer partitions. Now assume that both the balls and the boxes are indistinguishable, so when we distribute the balls into boxes, the only thing that matters is their numbers. In other words, we are interested in finding out the number of ways of writing the positive integer n as a sum of positive integers, where the order of the summands does not matter. That is, 4 is equals to 3 plus 1, or 4 is equals to 1 plus 3. Will count as only one way of writing 4 as a sum of positive integers. As the order of the summands does not matter, we do not lose generality if we assume that they are in weakly decreasing order. Definition 5.13. Let A1 which is greater than equals to A2 which is greater than equals to A3 and so on which is greater than equals to AK which is greater than equals to 1 be integers so that A1 plus A2 and so on plus AK is equals to n. Then the sequence A1, A2, and so on to AK is called a partition of integer n. The number of all partitions of n is denoted by P of n. The number of partitions of n into exactly k parts is denoted by Pk of n. We note that the word partition is used in a new meaning here. We have used it before in definition 5.5 to mean a way to split the set and braces. The new meaning given in definition 5.13 is independent of the old one. This double meaning of the same word usually does not result in a confusion as the context usually clearly indicates which meaning is relevant. In writing, so too does the notation. That is, we either speak of partitions of n braces or of partitions of n, if there is a danger of confusing after all. It is customary to refer to partitions of n braces as set partitions. We also note that some languages, like French, do have two different words for these two notions, partition for set partitions, and a partage for partitions of the integer n. Example 5.14. The positive integer 5 has 7 partitions. Indeed, they are 5, 4, 1, 3, 2, 3, 1, 1, 2, 2, 1, 2, 1, 1, 1, 1, 1, 1, 1, 1. Therefore, P of 5 is equals to 7. The problem of finding an exact formula for P of n is even harder than that of finding an exact formula for S of nk. If we know P of n minus 1 or, for that matter, P of I for all I which is less than n, we still cannot directly compute P of n from these data, though some sophisticated recurrence relations do exist, and we will mention them in the notes section. The approximate size of the number P of n is provided by the following asymptotic formula. P of n is approximately equals to 1 divided by 4 times the square root of 3 times e to the pi times square root of 2n divided by 3. In other words, P of n grows faster than any polynomial, but slower than any exponential function, g of n which is equal to c to the n, with c which is greater than 1. We will nevertheless find some interesting and useful results concerning P of n once we will have learned about generating functions. Until then, we will discuss some highly interesting and enjoyable identities. Our main tool is proving them will be the following graphical representation of partitions. A Ferrous shape of a partition P, which is equals to x1, x2, and so on to xk, is a set of n square boxes with horizontal and vertical sides so that in the ith row we have xi boxes and all rows start at the same vertical line. It is named after the American mathematician Norman MacLeod Ferrous. The Ferrous shape of the partition P equals to 421 is shown in figure 5.1. Clearly, there is an obvious bijection between partitions of n and Ferrous shapes of size n. If we reflect a Ferrous shape of a partition P with respect to its main diagonal, we get another shape, representing the conjugate partition of P. Thus, in our example, the conjugate of 421 is 3211. In particular, the ith row of the Ferris shape of the conjugate partition of P is as long as the ith column of the Ferris shape of P. Definition 5.15. A partition of N is called self-conjugate if it is equal to its conjugate. Example 5.16. Partitions 4321, 51111, and 4211 are all self-conjugate. Now we are in a position to use various shapes to prove various partition identities. Example 5.14 shows that the positive integer 5 has 3 partitions into at most 2 parts, 5, 4, 1, and 3, 2, and it also has 3 partitions into parts that are at most 2, namely 2, 2, 1, 2, 1, 1, 1, and 1, 1, 1, 1, 1. This is not by accident. Theorem 5.17. The number of partitions of N into at most k parts is equal to that of partitions of N into parts not larger than k. Proof: the first number is equal to that of various shapes of size n with at most k rows. The second number is equal to that of various shapes with at most k columns. Finally, these two sets of various shapes are equinumerous, as one can see by taking conjugates. Theorem 5.18. The number of partitions of N into distinct odd parts is equal to that of all self-conjugate partitions of N. Proof: we define a bijection F from the set of self-conjugate partitions of N onto that of partitions of N into distinct odd parts as follows. Take any self-conjugate partition pi equals to pi 1, pi 2, pi 3, and so on until pi t of N. Take its Ferris shape and remove all the boxes from its first row and first column. As pi is self-conjugate, this means removing 2 pi 1 minus 1 boxes. Set f of pi suffix 1 equals to 2 pi 1 minus 1. That is, make the first part of the image of pi of size 2 pi 1 minus 1. Then continue this way. That is, remove the first row and column of the remaining Ferris shape. This means removing 2 pi 2 minus 3 boxes. So set f of pi 1 is equals to 2 pi 1 minus 1 minus 3. Continue this way until the entire Ferris shape is removed. The resulting partition will be of the form f of pi equals to 2 pi 1 minus 1, 2 pi 2 minus 3, and so on, 2 pi I minus 2i minus 1, and so on. So it will indeed be a partition of N into odd parts, and the parts will all be distinct, as we had pi 1 greater than or equals to pi 2, and so on greater than or equals to pi t. We note that the set of all boxes consisting of one fixed box B, all boxes below B, and all boxes on the right of B is often called a hook. Using this terminology, we can say that in each step of our algorithm, we remove the hook of the box that is currently in the top left corner of our Ferris shape. To see that F is a bijection, it suffices to prove that for any partition alpha of N into distinct odd parts, there exists exactly one self-conjugate partition pi of N so that f of pi is equals to alpha. This is easy to see. Indeed, let alpha equals to 2a1 minus 1, 2a2 minus 3, and so on to 2au minus 2u minus 1. Then it follows from the definition of f that if f of pi is equals to alpha, then the first row and the column of pi must each contain A1 boxes. The second row and the second column of pi must each contain A2 minus 1 additional boxes, and so on. So we can build up the unique Ferris shape whose partition has image alpha, proving our claim. Example 5.19. If pi is equals to 6, 6, 4, 3, 2, 2, then f of pi is equals to 11, 9, 3. Figure 5.3 shows how f of pi is constructed. In step I, the hook consisting of all boxes labeled I in the various shape of pi is removed, and its boxes form rule I of the various shape of f of pi. Theorem 5.20. Let Q of n be the number of partitions of n in which each part is at least 2. Then Q of n is equals to P of n minus P of n minus 1 for all positive integers n which is greater than or equals to 2. Proof. We construct a bijection from the set of all partitions of n minus 1 onto the set of all partitions of n that have at least one part equal to 1. The bijection is very simple. Just add a part equal to 1 to the end of each partition of n minus 1. The only partitions of P of n that cannot be obtained this way are those enumerated by Q of n, so the claim is proved. We will not provide a formula for Pk of n here. Any such formula would be cumbersome anyway. However, we will see in Chapter 8 how to get a good description of these numbers. Let us try to find some connection between the number of partitions of the integer n and that of partitions of the set n braces. It is clear that the set partition 1, 2, 3, and 4 and 1, 2, 4, and 3 do have something in common. Indeed, they both consist of a block of size 3 and another block of size 1. We are going to generalize this notion as follows. Let pi equals to pi 1, pi 2, pi 3, until pi k be a partition of n braces, where pi I denote the blocks of pi. We arrange the sequence of block sizes size of pi 1, size of pi 2, and so on until size of pi k in non-increasing order to get the sequence A1 which is greater than or equals to A2, which is greater than or equals to A3, and so on which is greater than or equals to AK. Then A is equals to A1, A2, and so on until AK is a partition of the integer n. We say that A is the type of the set partition pi. Example 5.21. The set partition 156, 27, 39, 48, 10 is of type 3, 2, 2, 2, 1. Theorem 5.22. Let A equals to A1, A2, and so on until AK be a partition of the integer n, and let mi be the multiplicity of I as a part of A. Then the number of set partitions of n braces that are of type A is equal to PA equals to n choose A1, A2, A3, and so on to AK divided by the multiplications of mi factorial, where the multiplication is taken among all I which is greater than or equals to 1. Proof. Take AI balls of color I for all I in K braces. Order them linearly in n choose A1, A2, A3 until AK ways. Then partition n so that I and j are in the same block if and only if the linear order we just created has a monochromatic balls in positions I and j. This procedure clearly creates a set partition of type A. However, the number of different set partitions constructed this way is not necessarily and choose A1, A2, and so on to AK. For example, if A1 is equals to A2, then having the A1 balls of color 1 in a subset A of positions, and having the A1 balls of color 2 in a subset B of positions will result in the same partition as having the balls of color 1 in B and having the balls of color 2 in A. In general, if mi is the multiplicity of I as a part of A, then there are mi factorial ways the mi color classes having I balls each can be permuted among each other. Therefore, every set partition of type A will be obtained from exactly pi of mi factorial, where the multiplication of pi is multiplied for all index I which is greater than or equals to 1, linear orders, and the proof follows. The following table summarizes our results from this chapter when no empty boxes are allowed. For surjections, if the parameters are n distinct objects with k distinct boxes, then the formula is S of nk times k factorial. If the surjections, the parameters are n distinct objects, any number of distinct boxes, the formula are the summations of S of ni times I factorial, summing with I starting from 1 to n. For compositions, if the parameters are n identical objects with k distinct boxes, the formula is n-1 choose k-1. If the parameters of compositions are n identical objects and any number of distinct boxes, then the formula is 2 to the n-1. For set partitions, if the parameters are n distinct objects with k identical boxes, then the formula is S of nk. If the parameters are n distinct objects with any number of identical boxes, then the formula is the Bell number B of n. For integer partitions, if the parameters are n identical objects with k identical boxes, then the formula is pk of n. If the parameters are n identical objects with any number of identical boxes, then the formula is p of n. If empty boxes are allowed, then we have to fix the number of boxes. Indeed, if we do not, then we can add as many empty boxes as we want, yielding infinitely many solutions to all these problems. Therefore, instead of 8 different enumeration problems, we only have to treat 4. Their results have either been proved in this chapter or are trivial. Table 5.2 summarizes them. Enumeration Formulae if empty boxes are allowed. For functions, if the parameters are n distinct objects with k distinct boxes, then the formula is k to the n. For weak compositions, if the parameters are n distinct objects with k distinct boxes, the formula is n plus k-1 choose k-1. For step partitions, if the parameters are n distinct objects with k identical boxes, the formula is the summations of S of ni summing with I starting from 1 to k. For integer partitions, if the parameters are n identical objects with k identical boxes, the formula is the summations of pi of n summing with I starting from 1 to k. Notes: of the various enumeration problems discussed in this chapter, it is the enumeration of the partitions of the integer n that has been the subject of the most vigorous research. This problem proved to be interesting not only for combinatorists, but also for number theorists. The interested reader should see reference 4 for further information on integer partitions. A particularly nice classic result is the following recurrence relation due to McMahon. Let us say that a pentagonal number is an integer of the form k times 3k-1 divided by 2, where k is any integer, positive or not. So the pentagonal numbers are never negative, and the first few are 0, 1, 2, 5, 7, and 12. Then, for any positive integer n, p of n is equals to p of n minus 1 plus p of n minus 2 minus p of n minus 5 minus p of n minus 7 plus and so on, where the ith term of the right-hand side has sign minus 1 to the floor functions of I divided by 2, and the absolute value p of n minus ki, with ki being the ith largest pentagonal number. So, for instance, for n which is equals to 8, the above formula shows that p of 8 is equals to p of 7 plus p of 6 minus p of 3 minus p of 1, which is equals to 15 plus 11 minus 3 minus 1, which is equals to 22. Pentagonal numbers have other applications besides formula. The interesting reader can consult reference 7 for an application to permutation enumeration. Euler's famous pentagonal number theorem states that the number of partitions of n into distinct odd parts is equal to the number of partitions of n into distinct even parts as long as n is not pentagonal, and that these two numbers only differ by 1 if n is pentagonal. A precise statement of this theorem and its detailed proof can be found in the undergraduate textbook reference 6.